So in this video, we're going to do a couple of examples that demonstrate how you would use these equations to solve problems that involve constant acceleration. So first, I want to go over a little bit of problem-solving strategy, and I want to kind of summarize the equations in a little neater form. And here's what I'm going to do for you guys. This is my page of notes. We're just going to go off of that for this right here. And I think that is clear enough for you to see. All right, so these are constant acceleration equations, written hopefully in the same way that I wrote them before and derived them. And you can see what each one does not include here. So equation 1 doesn't include x. So if you're not given x and you're not needing to solve for x, equation 1 might be your guy. Equation 2, there's no v, right? And we could be talking in different directions. The x is not as important. It's just we're specifying that we're being consistent in our coordinate system. Equation 3, there's no t, so there's no information about time. Maybe you don't even need to know about time. It's not asking what happens at seconds equal, or when is the velocity, whatever, at what time is the velocity such and such. You don't need to know about time, and it's not given. 3 is a good equation for that. And there's no acceleration information in the 4th. And again, constant acceleration equations. So that's pretty much all we're going to be dealing with, because this is what we just derived. That's what we started with. That's what we're starting with. But as we go forward, it's important to know that you can't always jump back to these as a constant to solve for future problems. The only time they're relevant is if the acceleration is constant in your problem. So problem-solving strategies here. When you come across a problem, you might feel a little lost as to where to start or what you need to do. So usually you'd place the object at the origin, so x naught equals 0, right? That's why earlier I kind of expressed equation 4 as x naught just being 0. And usually you'd start the activity in your, whatever actions are taking place in your problem, you started at t equals 0. So there's no use specifying or accounting for any time before what's happening in your problem, because we don't care about that. So start everything off at x equals 0 usually, or t equals 0. And you want to pick a positive direction for x, and this determines, this choice decides the values for things going forward. So it determines the sign of your velocity going forward and everything else. So be alert for implicit information in the wording of the problem. So you might get something that says starting at a stop, so that would be x naught equals 0, or other things that we'll come across. And then when you read a problem, read it all the way through, but as you come across your variables, and these are the ones that we've been dealing with here, x naught, x, v naught x, vx, ax, and time. These are the quantities that we've been dealing with. You want to write them down as you come across them. So if it says starting at a stop, that means that v naught x is 0, and if you're starting at a stop, that's probably the start of your start of where everything is. So you might as well place whatever object that is, car, person, whatever it is, at x naught. And starting would indicate t naught, right? So t equals 0 at the start. And so there's other examples here, but start writing down your quantities as you come across them. And then find the equation that's missing the variable that you don't have. So you won't be given everything. You won't be given an abundance of information. You'll just be given usually the absolute minimum to solve the puzzle, right? Because these problems are kind of like puzzles, and you need to find which equation gets you what you want. And so, like I mentioned earlier, if you know nothing about acceleration and you're not being asked to solve for acceleration, then equation 4 might be a good one. On more complicated problems, you might need to bring two equations into it for just solving for one quantity. Oftentimes for each problem there'll be an A, B, C, different things, and they'll ask you for solve for different quantities, and you'll be using different equations for each of the parts. But even sometimes to find the target variable for a given part, you might need to use two equations where you have a set of equations and you have maybe two equations and two unknowns, or three equations and three unknowns. And as long as the unknowns are the same for all three, then it should work out. And then this is a big tip here: solve everything symbolically and then plug in the numbers. So you're going to get numbers that will plug in for these. That's how you get a numeric answer. But first you want to work everything out symbolically, and by that I just mean like what we did before. So we were working all symbolically in the last video. And so if you have 2x equals t over v minus v naught, and you were trying to solve for v naught, you don't want to plug in numbers right now. You want to move everything over and solve for v naught, right? So you'd have 2x v minus v naught is equal to t, which is 2x v minus 2x v naught equal t, 2x v naught is equal to negative 2x v t, v naught, we have 2x on both sides, v naught is equal to negative vt, right? So that's just gibberish algebra. But now, at this point, we've solved it symbolically, and we can go ahead and plug in whatever we have for v and whatever we have for t and solve for v naught. And notice, just like in this example, some things canceled out. And so you might get that, oh, I did something wrong, that's why it canceled out. This should be minus 2x. Well, whatever. You might have things cancel out, and it's very simple to solve it symbolically and then plug in numbers. And it'll save you some mistakes, much like what I just had. Because if I were carrying all that through and trying to carry through values, especially in scientific notation, and trying to carry units all the way through, I'd be using half a page just to get to the end result. And you're just more prone to mistakes that way. So, bring this back down. What was the last thing? Yeah, speaking of units, you want to evaluate your answer in the end and see if what you have makes sense. So if you have, if you're talking about a car and you get some, velocity at time equals 10 seconds to be 5 million miles per hour, well, you probably did something wrong, right? Cars don't go that fast. Or if you were trying to solve for time and you arrive at a magnitude where your units work out to meters per second, you can't talk about any time that is equal to a velocity. Those are two different quantities. So your units need to check out. So you should carry your units through carefully and make sure that you arrive at the units that you want, and check the magnitude and see if it's reasonable. All right, so that's a little bit of strategy, and the rest of it is just getting experience with these problems, and you see what works and what doesn't. And you begin to arrive at a procedure for yourself. As you go through them, they become more comfortable for you. All right, so we're going to go through this example that I'm about to put up here. You read. Example 2.4 here. And you, okay. So here's our example. A motorcyclist is heading east through a small town. Motorcyclist heading east through a small town accelerates at a constant 4 meters per second squared. So here we have our first quantity right there. So as soon as you see it accelerates at a constant 4 meters per second squared, there's two things that jump out to me. One, the acceleration is 4.0 meters per second squared. That's good. The next one, which is easy to forget, but it becomes more and more relevant as we move on, but the acceleration is constant. So that means we can, in fact, use our equations, our 4 equations that we derived. So acceleration is constant, and it's 4 meters per second squared after he leaves the city limits. And we're going to draw our own figure. At time equals 0, he is 5.0 meters east of the city limits. So here's an interesting one where our x naught, our initial position, is not going to be 0. So at time equals 0, when the scenario starts, his position, his initial position, right? Initial because time is 0, right? So that's what this naught stands for. His position is 5 meters east of the city limits. But we'll just say x is in that eastward direction from the city center, I guess, from that signpost. And he's moving east. So x is east. And at that initial time, right, this sentence is still applying to at time equals 0. His position is that, and he's moving east, right, at 15 meters per second. So that is v naught, because your time is 0. So v naught is 15 meters per second. All right. So I think we have all the basic information that they've given us before we read part A. And so at part A, for part A, they give us that find his position and velocity. So we're finding 2 quantities at t equals 2.0 seconds. So t equals 2.0 seconds. And A says find his position, so find x, right? X equals something. And to be explicit, you could say x at t equals 2.0 seconds, right? If that helps you remember what we're talking about. Or you could just write x. And we also want velocity at t equals 2 seconds. So at t equals 2.0 seconds is equal to something that we don't know yet. Right? All right, so let's start to draw this out. And I'm going to use a different color for our answer with that. All right, let's start to draw this out. So we have this eastward direction, which we're calling x, right? So here's our x-axis, and we're heading in this eastward direction here. This is x, which is also east. And that's, it's notable because velocity is a vector, so we are given that direction. All right. So this is x equals 0. This is x equals 0. But that's not where we start. X naught, so the position at t equals 0 is x naught, is not always is not always 0. It's oftentimes, but this one, right off the bat, we have an example where it's not. And so here, they've told us that x naught is 5 meters. So maybe somewhere around here. Yeah, 5 meters. Do a nice straight line here. And this is, do x naught equals 5 meters. Okay, that's x naught. And then his velocity at that time, and this is because we're talking about x naught, right? To be explicit, this is t equals 0. So this is when the time starts. He's at this position relative to, relative to the signpost. East of the city limits signpost, yeah. Okay. And we also have his velocity at this position. So v naught is equal to, what were we given? 15 meters per second. So that's when he's here. This is how fast he's traveling. Velocity at time equals 0. Yeah? Okay, and then we have some later time, 2 seconds. We'll just call that here. Yeah? So this is some later time, t equals 2.0 seconds. And we want to know the position there. We want to know after 2 seconds, how far has he gotten relative to the city limits signpost. And what we also want to know in A is his velocity. Velocity here. How fast is he going there? Right? Okay. So we can simplify this motorcycler to whatever we want to make it easy. We could just call him a particle, yeah? Let's call him this, because this is me in 2009 on my motorcycle. Believe it or not, that's 11 years ago. So that's me on my motorcycle. And I start here and I end there, yeah? So I'm on my way. And we want to know these two quantities. So which equation might be most relevant? Let's pull these equations back up here for a second. Which equation might be most relevant? We want to know position. We want to use position, and we want to know position. Then this one seems pretty intuitive, because it's already set up to solve for x. I don't know if that's big enough for you to see there. Equation 2 is already set up to solve for x. And we know something about the acceleration, it's given. And we know something about the time, it's given. And here's time again. We know v naught, and we know x naught. So we know everything that we need, and it's already solved symbolically for us to find the position. So let's go ahead and use that equation 2. Put this away for later. Let's go ahead and use that equation 2. Which is x is equal to 1/2 a in the x direction, right? We didn't write it. We could say a east if we really wanted to. But a t squared plus v naught, it's assumed in the x direction, times t again. Plus x naught. Plus x naught. All right, so there it is. So it's already solved symbolically, like I said, so we don't have to do any kind of algebra here. We can just arrange it. We can just plug on in. And so we get x being equal to 1/2. Acceleration was 4.0 meters per second squared. T is 2 seconds, and that's squared, plus v naught, the initial velocity that he was going at t equals 0 was 15 meters per second, times t again, so 2.0 seconds, plus x naught. Plus x naught was 5 meters. 5.0 meters. All right, hopefully that all fits on the screen for you just fine. So the units, right? If we're talking about x, x is a position, so we better end up, whatever we end up with on the right side here, it better work out to meters, right? You can only add like quantities. And so this one's good, it's already in meters. Well, this is the seconds on the numerator, the seconds on the denominator, so that's going to work out to meters. And this is seconds squared on the denominator, but we have 2 seconds, right? A second squared on the numerator here, because this t value is squared. So it should work out to meters. And if you work all that out, you should get that we're left with 43 meters. X equals 43 meters. We're only given everything to 2 sig figs, so I'm only reporting it to 2 sig figs. That's how that works. Right? If one of our values initially was just 1 sig fig, we'd have to go down to 40 meters, or 4 times 10 to the 2 meters. Okay, so now velocity. So now we want to solve for velocity. Do this. Let's bring our equations back up. Which one might we want to use to solve for velocity? A little bigger maybe. All right, we'll just go down the line here. Well, this one right off the bat has velocity, which is what we're trying to solve for, already symbolically ready to go. So do we have all the quantities we need on the right side then? Yes, we have acceleration. Yes, we have a t. And yes, we have a starting velocity. So perfect. We have everything we need, and it's already set up symbolically. So that's what we're going to do. We're going to use equation 1 here. So now we're solving for velocity. We're going to use equation 1, which is v, and let's assume that it's in the x direction. So v is equal to a t plus v naught. We can plug right in because it's already solved symbolically for us. So this was our acceleration, 4 meters per second squared times 2 seconds plus v naught, which was 15 meters per second. All right, so here we have seconds canceling with one of the seconds in the denominator, and this is left in meters per second, and this one's already meters per second, and so our units should work out. And what we would get if we calculated that is 23 meters per second for v. All right. So those were already kind of nicely set up for us to just use equation 2 and then equation 1, and it was already all solved up for us. It doesn't always work out that way, but sometimes it does. So now B, part B of this problem, let me go back up here, snag this guy. Part B said, where is, here, I'll bring it down here, and we'll just go from there. All right, so now, bear with me. All right, where is he when his velocity is 25 meters per second? What position is he at, right? So where, that's position. What position is he at? So x equals what when his velocity, v, we're not talking about initially, we're talking about some later time, is equal to 25 meters per second. Right? So we're going to be some way further down our eastward direction. So this is B here. Okay. So which equation should we use? Which equation helps us here? So we want to know position, and we have V, and we have the other things that we have already used as well. So we have a new velocity, right? So this one, we could use this one, but we don't know the time at the point that he reaches this velocity, right? We don't have any information about time. We're not talking about 2 seconds anymore. So that one doesn't quite work because we wouldn't have t. We would have a because that's a constant, so that applies to any time in this whole thing. And we have v, and we want to know x, and we have v naught, so that the rest of it works, but we don't have t, so 1 is out. Oh, never mind. Yeah, this is not x, this is v naught x, so we don't even have x in that equation, no x, and so it wouldn't even solve for what we want. And then 2, x equals, well, that's looking promising so far, but look at all these t's in here that we have, and we don't know what t is at this point, so we can't use 2 either. So now here we have vx, so that's something we have because we have what is its velocity, or what is its position when its velocity has reached 25 meters per second. So that's vx, so we have that. And we have v naught x, right? We have v naught. We have a, of course, and here's position. So that's what we're looking for. We'd have to solve and do a little work for it, but that's what we're looking for. And we have x naught. So that totally works. And exactly, it says no t. We don't have time. We don't know when this occurs. We just know that it does at some point. And so that might work perfectly for us. So let's give that a try. Sometimes there's more than one that works, and you can keep going and evaluate. Maybe another one is better, but I see immediately this next one has t, and so it would not work. So 3 is the only one that I see that would work for us here. So our equation 3 is v squared. It's assumed we're talking about in the x direction, which is east in this problem, is equal to v naught squared plus 2a in the x direction, of course, times x minus x naught. All right. So we don't want to plug in numbers yet because what we're solving for is this guy here. We're solving for that guy there. And so he's pretty hidden right now. So we want to do some algebra and get him out of there so that we have x equals whatever else is on the right side, right? So v squared minus v naught squared is equal to 2a x minus x naught. Yeah. We have v squared minus v naught squared over 2a is equal to x minus x naught, getting closer. And we'll switch these things here. So x is equal to v squared minus v naught squared over 2a plus x naught. Now we can plug in our quantities because we've solved symbolically, and it's very easy to plug everything in, right? So we have x is equal to our velocity, which is 25 meters per second, right? 25. This was given in part B. So at 25 meters per second, when his velocity has reached this value, what is his position? So that's the 25 meters per second minus v naught. His initial velocity was, I don't even remember. His initial velocity was 15 meters per second. And that's also squared as per our equation we figured out. Divided by 2 times the acceleration, which I believe was 4 meters per second squared. 4.0 meters per second squared. And don't forget this plus his initial position, which is not 0 here, it's 5, I believe. 5, yes, 5.0 meters due east. Yes. All right, So if you solve all of that out, you get his position when he reaches 25 meters per second is 55 meters. All right. So that is our first example here. I'm going to toss some of this away. And here, in my next page of notes, we'll do another example. Rearrange everything. Ready to move on to the next one. Get it way up out of the way. All right. Next page and example. All right. So this example, we have another vehicle type one. They're nice problems to be able to regulate the velocity. So the acceleration could be constant if you're just keeping your foot at the same place on the gas pedal, right? So here we have a motorist traveling with a constant speed of 15 meters per second. So V of the motorist, so I'll do Vm, which doesn't refer to the direction. It refers to the velocity of motorist, M for motorist. Vm, 15 meters per second. And notice it says constant speed. So this is not constant acceleration, this is speed, different quantities. So his speed is not changing. So that means whatever his initial speed was, it's equal to, right? So Vm naught, his speed at time equals 0, is the same as his speed at all other times. So Vm naught is equal to Vm, which is equal to 15 meters per second, which they tell you is about 34 miles per hour. He passes a school crossing corner where the speed limit is 10 meters per second. So he is speeding. Just as the motorist passes the school crossing sign, a police officer on a motorcycle will stop there. So we have another moving thing, another moving vehicle. So we have a police officer that's on a motorcycle. We're gonna shorten that to P for police. So he's stopped there. So his, do like this. So VP, not P for police. So the initial speed of the policeman is 0 because he is stopped. He starts in pursuit at a constant acceleration of 3 meters per second. So A, the acceleration of the policeman, is a constant 3 meters per second squared. So it's good that it's constant, so we can use our equations. It's always good to check. And then we're going to draw our own figure. And then part A, how much time elapses before the officer passes the motorist? So A says how much time. But let's go ahead and draw our figure first. Huh? So we have, let me use another color so that this is kind of like our work here. So we have some line here that signifies position equals 0. And we have some direction, some axis that they're traveling in, yeah? And since we'll refer to position as x, we're going to call that the positive x direction, right? So we have here a school crossing sign. I'll put that here. school crossing sign is right here. A little crosswalk, yeah? Maybe that makes some sense. And that's going to be, for us, we'll call that x equals 0. So this is x equals 0 and t equals 0 because when you go back to the equation, or to the problem, everything starts once the motorist passes that school crossing sign. Yeah? That's when the action starts. A motorist traveling at a constant speed of 15 meters per second passes a school crossing corner where the speed limit is blank. And just as the motorist passes the school crossing sign, a police officer on a motorcycle, which is also stopped at the school crossing sign, starts in pursuit. So that's x equals 0, yeah? And so the policeman starts here, and so we can write some other things down, I suppose. So x naught, or xp naught, the initial position of the policeman is 0, and the initial position of the motorist is equal to 0. But the difference is the motorist is already carrying some velocity, whereas the police has to accelerate from a stop at an acceleration of 3 meters per second. So the policeman is a motorcyclist, so of course, let's call me the policeman here. And this is at some further, time later. But this is the policeman. Police. Because he's the motorcyclist, motorcycle police. And so whatever position he's at this point here, that's the position of the policeman. Yeah? And he's going this way, right? He's going this direction. And he's accelerating. He's accelerating at 3.0 meters per second squared. That's his acceleration. And then we have a motorist that he's trying to catch. So we're going to put the motorist ahead of him. Eventually he will catch him, and justice will be restored. But for now, we're going to say the motorist is quite a bit ahead of him. And so this here is the position, x, of the motorist, xm. And the motorist acceleration, so he's also traveling this way, but the acceleration is 0, because he's traveling at a constant speed. And let me see if I can, let's do this. Let's color code some things here. So if we're talking about acceleration, let's talk about it using pink. So he's acceleration, A, of the policeman is 3.0 meters per second squared. And his velocity is constantly changing because of that. He's accelerating. So his meters per second are updating each second. Whereas the velocity, I don't remember what we used a video ago, but maybe it was yellow. I can't remember. But we will call velocity yellow here. So this guy has a velocity that's in this positive x direction. V is equal to 15 meters per second. But his acceleration is 0. He's not accelerating, right? So A of the motorist equals 0, right? And this velocity here is, of course, v sub m for the motorist. And the velocity here is changing. So he, of course, has some velocity, but it's Vp is increasing. So at different times, different positions, his velocity will be different. So there's no use specifying it at this random point that we've imagined him to be at this moment. Okay. So what is this problem asking for? So we have part A. How much time elapses? So I'll go back to my red here. How much time elapses before the officer passes the motorist? So the officer passing the motorist, what would need to be true for the officer to pass the motorist? There's a lot of things that we might suppose to be true. We could guess the appropriate velocity that the police would be at the point. But the thing that quite simply needs to be true is they must be at the same position. If the policeman has caught the motorist, then they're at the same position. So that means that what we are solving for is the moment that xp, the position of the policeman, equals xm, the position of the motorist. That's the moment that we're analyzing. xp equals xm. And part A is asking, given that, what's the time that has elapsed? What is t when that condition is met? So this is our condition, and here's the variable we're trying to solve for. All right, so which equation should we use? Or could we use? So we want to know t. That's the variable we are curious about. And we have some other variables going as well. Which equation should we use? Okay, well, equation 1 doesn't have position. It has no x, and that is the condition that we're talking about. So position is very relevant. We have position going on. We need to say when the position of the motorist equals the position of the policeman. So 1 probably wouldn't be very helpful. Equation 2, x is equal to, okay, we have some t's in here, so we can solve for the t. And we have a, we know a, at least for the, well, we know a for both. It's 0 for the motorist, and it's something non-zero for the policeman. And x naught, we know x naught for each of them. So it looks like 2 is our winner. So we can solve for t. And here's a little bit of a trick here. So for each of these, we have 2 different values, right? For acceleration, we have an acceleration for the motorist and an acceleration for the policeman, and they're both in the x direction. So there's a lot going on here. But this equation works independently for each of the moving bodies. And so we can solve it and handle each of the different moving bodies separately. But one thing that we do know is that the position is equal at the time that we are looking for. And so if this is x, well, if it's xp or xm, whichever, they are equal. So what we can do is set equation 2, both variants of equation 2 with our policeman and our motorist, we can set them equal to each other because xp is equal to xm. Their positions are the same. So we can use equation 2 for, let's do first the motorist. So xm is equal to 1/2 a of the motorist times t squared plus v of the motorist, and this is all in the x direction, it's implied. We're working on a linear path, the road is straight, times t plus the initial position of the motorist, so xm naught. Oh, this is the initial position of initial velocity of the motorist here. There we go. And then separately, we have position of the policeman is going to be equal to 1/2, same equation, acceleration of the policeman times t squared plus the initial velocity of the policeman, vp naught, times t, plus the initial position of the policeman, xp naught. And we can set these things equal to each other. So let's go ahead and do that. So we have 1/2 am t squared plus vm naught t plus xm naught equals, let's slide it on over, equals 1/2 a p t squared plus vp naught times t plus xp naught. Might seem like a lot, but let's look at it. What is the acceleration of the motorist? You remember? Let's go back up. Acceleration of the motorist. 0. 0. So in our equation down here that we have going, if this is 0, then this whole term is 0. Okay, there we go. Its velocity is not 0. It's going at 15 meters per second, I believe is what it was. Yeah, I failed to write it earlier, but that's what it is. And x naught is going to be also 0. They each start x naught. Their position is when they pass each other initially, and so that's 0. So that term drops out as well. And then acceleration of the policeman, that's non-zero. That's 3 meters per second squared, so we keep that. But the initial velocity of the policeman, well, he starts at a stop, right at that school crossing sign. So this is 0. And then finally, also the police's initial position. He starts at x equals 0. So that term is 0. So look at that. We're left with something quite a bit simpler. So what we have is Vm naught times t is equal to 1/2 AP t squared. And that's it. That's what we're left with. So now, what we were wondering was the time. At what time does the policeman catch the motorist? So we can solve for time as we can set Vm naught t minus 1/2 AP t squared equals 0. Factor out the t. So t Vm naught minus 1/2 AP t equals 0. And so really we have two answers, which might have escaped you if you hadn't looked too carefully. We have two answers. Why do we have two answers? Why is one of our answers t equals 0? Well, their positions are at the same time at t equals 0. When the motorist initially passes the policeman, he passes his position. So they're at the same position at t equals 0. We weren't even really considering that we were solving for that, but that is a time that the positions were the same. But the question is strictly asking what is the time when the policeman catches the motorist? And so the true answer is this other one. T is equal to 2 Vm naught divided by AP. Right? And if you plug that in, you get 2 times 15 meters, I think it's getting bigger, per second, divided by the acceleration of the policeman, which is 3.0 meters per second squared. And if you work that out, the other time that they're at the same position, when the policeman catches the car, you have t equaling 10 seconds. So that's the other true answer that they were looking for. So that one was a fair bit trickier because we had two motorists, or two moving vehicles. One we called the motorist, the other one the policeman. And so we had to handle each of their variables separately with different sub-letters to designate each. Let's pull this back down and we'll get the problem again. So for B, let's see, what is B asking in here? What is the officer's speed at that time? All right, so now we have t equals 10 seconds, the time that he catches the motorist. And how fast does the officer end up going at the time that he catches the motorist? So for C, I'll change colors here just in case you're getting tired of the red. Let's go green. And now for part B, we have t is equal to 10 seconds. That's what we solved for. And what is the speed of the police officer at that time? That's what we're wanting to know now. Yeah? So now, which equation should we use? Let's pull this back up. It's really worth it, as you can see, to jot this down really neatly in pen or something on a piece of paper that you can reference as you're doing problems to see the equations and which one might work for you. You might have it just right on the side at all times when you're doing problems. You can just refer to them. You'll get real familiar with these as well after you do a few. So let's see, we are wanting to solve for his speed, Vp, at t equals 10 seconds. And we have some other information buried in the problem from earlier as well. So we're wanting his speed. Well, here we have speed of something is equal to the acceleration of it, which we have for the policeman, times the time that we're worried about, which we have, that's 10 seconds, plus its initial velocity, which we have is 0, and that's all. So we have everything we need. So equation 1 seems to do the trick. We have not used equation 4 yet, I remember. I wonder if we will get a chance to use that soon. So equation 1 is the one. So equation 1 goes like this. V of the policeman is equal to the acceleration of the policeman times the time that we're worried about, plus V of the policeman initially. It's already solved for us symbolically, but let's see if we can just cancel something out. That we said is 0 because it started at a stop. So we don't even have anything to plug into that. So really we have Vp equals AP times t. And so if we plug in our 3 meters per second squared times t equals 10 seconds, so we worked hard to solve for on part A, then we get Vp, the velocity of the police officer, being equal to 30 meters per second when it catches the motorist. All right. And specifically, it asked for the speed. I'll go back to confirm. It didn't ask for the velocity of the motorist or of the police officers. It said, what is the speed? And of course, colloquially, we would refer to speed and velocity as about the same thing if you were talking to your buddy over a sandwich. But in physics, when it says speed, that is specifically meters per second, but we're not talking about direction. So if we had defined our axis in such a way that this was the negative x direction, we would have worked out the velocity of the police officer as that 30 meters per second, but in the negative x direction, so negative 30 meters per second, right? Because if this is the negative direction, it's going in this direction. We've just flipped our axes, right? We just defined it in a purposefully difficult way for no reason, of course. And we get negative 30 meters per second. And so if it were asking about the speed, it doesn't want direction. It just wants the magnitude. And so therefore the negative was only referring to the direction. And so we would take the absolute value. But of course, since we defined our axes in such a way that was nice and simple for us, that they're traveling in the positive x direction, then when we got 30 meters per second, it was already positive. So we don't have to think too hard to take the absolute value of this and say that the speed of the police officer, speed sub p, is also equal to 30 meters per second. It's a subtlety, but there is a big difference between velocity and speed. Okay, and then part C. What does part C say? Last part of this problem here. Part C. At that time, so 10 seconds again, what distance has each vehicle traveled? So now we're asking about position. And before we said, well, xm equals xp. But now we're saying, well, what really is xm and xp? So we know that xm and xp are going to be equal because that's what we mentioned before. Let's see, what color haven't we used in this one? We used blue, purple, red, yellow, green. I have a full color wheel in front of me and I'm feeling like I'm running out of colors. We just did green, can't go with that. Let's go with orangey kind of color. Orange. Okay, so part C says, what is the position of the policeman, right? And what is the position of the motorist? Well, it's still true at the time that the policeman catches the motorist. It's still true that their positions are the same. And so it's still true that xp, the position of the policeman, is equal to xm, the position of the motorist. So it's kind of like they're asking two different things, but they're asking for something that we know is the same. So what is the position of each of the vehicles? Well, they're going to be the same. So we don't have to do one calculation here. But which equation should we use? Pull out our equations. So we want to know position, right? And we have almost everything else. So it should be easy. There might be a few that we can use. Okay, so this one we cannot because we're looking for position. This one doesn't include x, right? So that one's out. This one does have x. It has acceleration, right? So for the motorist it'd be 0, but for the policeman it'd be 3 meters per second squared. It has time, which we know is 10 seconds. And initial velocity for each, we know that. Time again, and then initial position. So we can use 2. And you can go ahead and try using 2, but since we haven't used equation 4, I'm going to check to see if we can use equation 4 here, just to change it up. Just to change it up. So here, we're looking for position. X minus x naught. Well, x naught for both of them is 0, so we're good so far. The initial velocity we have for both of them. The initial, or the final position, or velocity, we have for both of them because the car isn't changing velocity, so it's 15 meters per second. And the policeman got to a speed of 30 meters per second. He's going twice as fast by the time he reached him. Divided by 2 times the time. So we can use equation 4. It's perhaps no easier or harder than equation 2, but we can use it, so let's do it. So equation 4 here. Right. Get rid of my little lines floating in space here. Okay, so for equation 4 we have, and let's go with the motorist, huh? xm, position of the motorist, is equal to, or minus xm naught, which we know is 0, but we'll write it out there just to be complete, is equal to v motorist initially plus v of the motorist at that later time divided by 2 times t. So if this is equal to 0, we really don't have to do any more work symbolically. That's already going to be the only thing left on the left side of the equal sign. And we can just go ahead and plug on in. So x the motorist, the position of the motorist, right, is equal to Vm naught. Initially, the motorist is traveling 15 meters per second. And it is not accelerating. The acceleration of the motorist was 0. It travels at a constant speed. So the speed when the policeman catches him is still 15 meters per second. He really didn't react too much to the policeman coming after him. You would think he would either slow down or make a run for it, huh? Divided by 2. And the time, t, is 10 seconds, which is what we solved for in part A. Yeah. 10 seconds. All right. And if you compute all of that out, you get that their position when the policeman catches them, xm, which is also equal to x of the policeman, of course, is equal to 150 meters. They've traveled quite a distance there. Quite a distance. Yeah. So go ahead and try to solve the same thing as part C here, but using equation 2, and see if you get the same answer. You should. And so it's a good demonstration that more than one equation might be able to work. And so you want to choose the best one or your favorite one if you have multiple options. All right. Let's see, that is page 18. I think I only have one more small thing to cover. So here we go. I'm going to get rid of these notes to rearrange. I've gotten better at this from last video. So we're going to put this where we want it. And then pull out my notes now and put it where I want it. So only a couple more seconds here, but in free fall, that's an example where you have constant acceleration. I kind of mentioned it briefly before, but since you will be doing problems with it, it's worthy to point this out explicitly. So in free fall, acceleration is constant, and it is equal to, on Earth at least, g, the gravitational constant, g, which is equal to 9.8 meters per second squared. I would give you more precision, but it varies based on elevation. So the closer you are to the core of the Earth, the greater it is. The farther away you are, the lesser it is. So here in Flagstaff, it might be 9.79, I'm not sure, I'd have to look it up. Or it might be 9.80 something, whereas at sea level it might be 9.81, which I think is closer to the actual value at sea level. But it's also important to point out that the acceleration is constant. This is something that we've kind of been getting accustomed to in our problems here. But when something is falling down, the acceleration is constant. It doesn't increase as you get, well, like I just said, it does increase. But if you're talking not miles and just meters or something, it doesn't increase enough for you to consider. But a classic problem and kind of difficult concept for people to get is if I throw a ball upwards and it follows this path, like this, right? It comes down to where it was. I guess I got too many. Comes down. What is the acceleration at various times here? So this is a ball we're throwing on Earth, right? And this is just about where my hand is here, and I toss it up, and it goes like this. What is its velocity, and what is its acceleration at various points on this path that it takes? So if we say that we got to define a coordinate system, of course. So we're going to say this is positive x. Positive x. Yeah? And we won't worry about the fact that it's traveling another direction there. We're just staying up and down. If I threw it straight up and straight down, it'd be the same, but I couldn't draw that layering over itself very easily for you. So it's going, this is a positive x direction. So that dictates what the sign of our velocity is. When I initially throw it, it has some velocity that is positive. So when I initially throw it, I give it some initial velocity, really, that is positive, something or other. And after it leaves my hand, it's no longer accelerating due to any force that I am giving it, but it's accelerating due to another force. Well, this ball has mass, and gravity acts on mass, and gravity pulls it down to Earth. So it has some force downwards, right, from gravity that's acting on it. And that is constant throughout. The force is a constant force. So acceleration is equal to gravitational acceleration, and that is downwards, right? You can do this, downwards, right? And so the acceleration when the ball is here, just a moment after it leaves my hand, acceleration is downwards. The velocity is positive. It's still going in a positive x direction, right? The v is positive. How about here, though? This is the quintessential conundrum, right? So here, the ball has reached its peak point. And if we're only talking about vertical velocity, not considering left and right motion, vertical velocity, is it traveling up or down? Well, its velocity right now, here, it comes to some peak, and at some moment in time, the velocity is 0. Yeah? The velocity is neither up nor down. Right? If you can imagine throwing up a ball, it pauses at the top for a moment before it comes back down. But what is the acceleration? The velocity is 0. Is the acceleration 0? No. No. Gravity doesn't shut off just because it's reached the top of its path. Acceleration is still downwards, or negative. Right? Acceleration is still negative, just like it was over here. Equals negative, and specifically 9.8 meters per second squared. And specifically here also, it's negative 9.8 meters per second squared. Hopefully that shows up. Right? And then over here, now the ball is going downwards, and so its velocity is now something negative because it's traveling in this direction, which is downwards on this vertical x scale here. So velocity is negative. What is acceleration? It's the same thing. Gravity does not change just because the ball is moving around in the sky. It's negative 9.8 meters per second squared. And then even here, if I were to say I catch it, right, in my hand, I catch it, the net acceleration can be 0, but gravity still applies. So my hand is counteracting by giving a force to counteract it, to keep it at the same level. But we'll talk about that when we get to future chapters, when we apply Newton's second law. But that's just a taste of what we're talking about when we talk about free fall and how constant acceleration really truly does apply to a lot of real-world phenomena. All right, see you in the next video. Thanks for sticking with me on this longer one. We'll talk next about velocity and position by integration, and that'll be it. See you.